What's up, guys? My name is IBM, and my IGCSE students asked me to solve February March papers, and they asked me specifically to solve alternative to practical, that is paper 6. So, because it is a very simple paper and I got some 1 hour to solve this, I decided to solve this today. So, without wasting time, I would like to take you to the question paper. Find the question paper in the video description. So this is Feb March. It's October, November. Feb March 2024, paper 6 to. This is especially for students in India. So this paper will give you a guide to what you expect in the upcoming exams in paper 6. So question number 1, student determines the mass of a meter rule by balancing method. He's using the apparatus shown. So this is the apparatus. The student places a circular load on the meter rule shown in the figure 1.2. So this is the figure 1.2. Determine the distance d of the center of the load from the zero end of the rule as shown in the figure 1.2. Figure 1.2 is not to scale. So we want to measure the mass from the center to the zero end. So first of all, we just need to find where the center is. So on this side of the mass, I think it is here. And on the other side of the mass, I think it is here. So this is, the scale is 25, 26. So this is 26.1.2.3.4.5. So this is 26.5, and this is, I'm going to subtract, this is 29.9, 29.8. So 0.8, 29.7, 29.6. So this should be 29.5. So I want to find the center from the other end, from the zero mark. So the center is going to be 26.5 plus 29.5, divide this by 2. So 26.5 plus 29.5 divided by 2. This gives me the center. So this is going to be 28. Remember, this is the distance from the zero end to the center of the mass. So this distance is 28 centimeters. So I'll write, because the distance from a meter from a ruler is measured to 1 decimal place, I can also write 28.0 centimeters. Then the student adjusts the position of the meter rule on the pivot until the meter rule is as near as possible to being balanced. Describe a technique for ensuring that the rule is as near as possible to being balanced. Of course, the technique is very simple. You just note the point where it tilts on one end, and then the point where it tilts it just tips on the other end. So it means the balance point must be between these two positions that you have determined. So note the point where it just tips one way. You note that point where it just tips one way, and then another way, another point where it just tips the other way. Another point where it just tips the other way. So it means the balance point is between these 2 points. The balance point must be between these 2 points. So the balance point is between a point where it just tips on one side and where it just tips on the other side. The balance point must be in between there. Then the student finds that the rule is as near as possible to being balanced when the pivot is at the 47.6 centimeter mark. When the pivot is at the 47.6, the pivot is at the 47.6 centimeter mark. That is from the zero mark. Okay. Calculate the distance A of the center of the load from the 50 centimeter mark as shown in the figure. Use your answer of D from A, and the equation A equals 50 centimeters minus D. So it means A is going to be 50.0 minus D, which was 28.0. I think without wasting time, this is going to be 22.0 centimeters. Then calculate the distance B of the center of the load from the pivot as shown in the figure 1.1. Use your value of D from A, and the equation B is equal to position of the pivot minus D. So B equals the position of the pivot. They say the position of the pivot was the 47 centimeter mark, 47.6 minus D, which was 28. So I think 47.6 minus 28, that is 19.6. So B is going to be 19.6 centimeters. Then the student moves the load so that its center is above the 5.0 centimeter mark and balances the meter rule. He repeats this procedure for the load at the 10.0 centimeter mark, 15.0 centimeter mark, 20.0 centimeter mark, and 25.0 centimeter mark. His results are shown in the table. So this is the table of results. Okay, plot a graph of A centimeters on the y-axis. So I will label this on the y-axis. I would say A in centimeters against B in centimeters on the x-axis. So I'll put here B in centimeters. Then you do not need to start your axis at the origin 0, 0. So draw the best fit straight line. So first of all, many times I encourage my students to draw the axes, even though they will not really be very important. But you can always draw the axes to give a good impression to the examiner that you really know what you're dealing with. It doesn't require you to put their x-axis, y-axis, but you can indicate the axes there. So you don't need to start from 0, 0, so that means I can choose an origin of my own. For example, on the x-axis, I look at the values I will plot on the x-axis. The smallest is 22.5, so I can choose my origin to be 20.0. So I can say this is 20.0 as my origin on the x-axis. Then on the y-axis, the smallest is 25. I can still make 25 to be the origin here. So I can say this is 25.0. Then choosing the scale on the vertical, it is easy to choose. You have 25, 30, 35, 40, 45. The scale on the vertical can just be 5. So I can say after every 5, 10 small squares. So this would be 30.0. Then this will be 35.0. Then next would be 40.0. And then 45.0. Then on the x-axis, looking at the values, I can just guess the scale, but if you want to now to find a scale, you can say the highest is 40.5 minus the origin, which is 20.0, divided by 1, 2, 3, 4, 5. Divide this by 5. 40.5 minus 20 divided by 5. So when I round off that, the scale is going to be approximately 5, because the scale must be rated to 1, 2, 2.5, and 5. This one is giving me 4.1. I round off the next number there, which is going to be 5. So next should be 25.0, then followed by 30.0, 35.0, 40.0, 45.0, and so on and so forth. So now I start plotting. The first point was 45 and 40.5. So 45, 40.5, 45 on the y, 45 is on the y-axis, then 40.5. So the scale on the x-axis is 1 square, on the x-axis is 0.5. So because it's 5 divided by 10, which is 0.5. So 1 square on the x-axis is 0.5. So 40.5 is going to simply be a point here. The next point was, I think, 40 against 35.2. So 40 against 35.2. So 35.2 is very close to 35. So I'll just plot it around here. Then the next point was 35 against 31.5. 35 on the y-axis against 31.5. So each box is 0.5. No, each box is 0. Did I say 0.5? 20. Yes, each box is 0.5. So I want to plot 31. Those are 3 boxes, I think. 30, 31.5 against 35. So 1, 2, 3. So it must be this point here. Then the next point is 30 on the y-axis against 26. 26 are 2 boxes, so the point must be this one. And the last point is 22.5 on the x-axis, 21, 22.5 against 25. So the point must be here. Okay, so that is the point. Of course, I drew a circle which goes upwards because it is just at the edge there. So the next thing is to draw the line of best fit through these points. So the line of best fit. So for the line of best fit, you try to balance the points. Okay, I've tried to balance the points, but I want to make a line which at least touches a few of these points. Okay, I'll go with that. Of course, the line of best fit must have these points balancing around the line of best fit, almost balancing around the line of best fit. So that is going to be my line of best fit. It may not be the best. You can draw a better line of best fit on your question paper. Okay, so they say draw the line of the best fit line. I've drawn that. Then determine the gradient of the graph. Of course, for the gradient, make sure you draw a triangle. Otherwise, if the triangle is not seen, then it becomes a problem. And the triangle must be big enough. So to draw the triangle, we look for points where the grid lines cross with the line. So for example, I'm taking this point here. The grid lines are crossing and they are crossing through the line. Then I'm also going to take, say, this point here. Let me take a point, say this one. Your triangle should be as big as possible. So I'll take these points as the points for my triangle, and I'll draw my triangle through the points. So that is going to be the triangle for which I'm going to use to find the gradient. So if I want to write this point here, I think this is 20, 21, 22, 23, 24.5. That is 24.5 against. On the vertical, this is 25, 26, 27, 28. Then on the this point here, this is 1, 2, 31, 36, 37. So this is 37. Then on the vertical, it is 41.5. Okay, so we can find the gradient. So G is going to be 41.5 minus 28.0 divided by 37 minus 24.5. So I just check with my calculator. 41.5 minus 28 divided by 37 minus 24.5. So I'm getting approximately 1.08, or you can write 1.1. Of course, this will have no unit because they said show clear on the graph. That means you must show a triangle, or you must write points there. So you could write 1.08 or 1.1, or any value very close to 1.08 would be your gradient. Then calculate the mass m of the meter roll using the equation m is equal to k over g minus 1. So I will just substitute m is equal to k, which is 25 grams, divided by g. We have got g as 1.08, then minus 1. So this is going to be, of course, g has no units. The gradient had no units because on the vertical it was in centimeters and on the x-axis is in centimeters. So the gradient has no units. So here I have this or that, but I will take 1.08. So this is going to give me, say, minus 1. Then I'll say 25 divided by the answer. So that is 312.5, or approximately 313. I'll just write approximately 313 grams. Then the accuracy of the result obtained by this procedure depends on the meter rule without a load, balancing with the pivot at the 50 centimeter mark. A student finds that this does not happen. She adds a small piece of modeling clay to one end of the meter rule to correct it. In other words, she's adding a small piece to ensure that the meter balances at the 50 centimeter mark. Suggest if this is a suitable change for this experiment. So there are two ways of this to think about this. Either one, you can say no because the mass of modeling clay would increase the mass of the meter roll. So it's not a suitable method. Alternatively, you can say yes, because if it is a small piece, then its mass is only a very small percentage compared to the mass of the meter roll. So it doesn't affect the results. So you have two ways of answering this. So you can say no, because the mass of modeling clay increases the mass of the meter rule. You can think about it like that. But on the other side, you can also say yes, or you can agree. But when you say yes, you can say yes, that it is a suitable change for this experiment. So you are saying yes because the mass of a small piece of modeling clay could be only a small percentage of the mass of the meter rule. Yes, because the mass of modeling clay could be only a small percentage of the mass of a meter rule. So the mass of a meter rule could be, for example, here we have used the 313 grams. So the mass of a meter rule is approximately 313 grams. So if you use, let's say, small piece, 2 grams, so it means 2 grams is a very small percentage compared to the mass of the meter rule. Question number 2 is electricity. A student investigates a circuit containing different combinations of 3 resistors. She first uses circuit A as shown in the figure. So we see we have 3 resistors in series. On the figure, draw a voltmeter connected to measure PD for terminals P and Q. So we connect a voltmeter across between P and Q. So I'll put my voltmeter here. The student measures the potential difference V for terminals P and Q and measures the current I in the circuit. The meters are shown in the figure 2.1 and 2.3. Okay, so this is the scale here is 0.123. Okay, so the scale is 0.1 here. Each small division 0.1, so this should be 3.1. The scale here is 0.2 divided by 10, which is 0.02. So because from 0 to 0.2 we have 10 divisions, so the scale is 0.02 for each division. So this is 1, 2, 3, 4, 5, 6. So I'll say 6 times 0.02, which gives us 0.12. So this is at 0.12. Read and record in the first line of the table the values of V and I shown on the meters in the figure. So of course V is measured in volts, current is in amperes, resistance is in ohms. So circuit A, the meters are shown in the figure. The student measures the PdV for points P and Q. Okay, so these are the current. The current is 0.12 and the voltmeter reading is 3.1. Okay, read and record in the first line. So we have recorded. Then circuit B, the student connects the resistors between terminals P and Q as shown in the figure 2.4. She measures and records in the table 2.1 the values of V and I. So circuit B, the values have been recorded. Circuit C, the student connects the resistors between terminals P and Q as shown in the figure. She measures and records in the table the values of V and I for this circuit. So she records the values for circuit C in the table. Then calculate and record in the table a resistance R for each circuit. Use the values of V and I from the table, and the equation R is V over I. Add units to the column headings in the table. So I have already added the units. Voltmeter reading is in volts, current I is in amperes, resistance is in ohms. If you don't know the symbols, you may write in words, volts, amperes, ohms, but the space is just enough for letters. So for the first, we are using the equation R is equal to V over I. So I'll just press my calculator. The first one is 3.1 divided by 0.12. I can't write to less than 2 significant figures because each of these is to 2 significant figures. 3.1, 0.12, those are 2 significant figures. So I'll write my answer to at least 2 or more. So I'll write 25.8. The next one is going to be 2.9 divided by 0.22. 2.9 divided by 0.22. So that is 13.2. Round off correctly. Then 2.6 divided by 0.86. So this is going to be 3.02 ohms. So there's consistency here for three significant figures. Okay, circuit B, we have finished this page. I'll just go straight to page 8. D. Calculate a resistance RA using the value of R from circuit A. I think R from circuit A was 25.8, so I'll say RA is equal to 25.8 divided by 3. 25.8 divided by 3. So this is 8.6 ohms. Then B, use the value of R from circuit B and that equation. So RB is equal to what was R? What was R? I think it is 13.2 and 3.02. So this is 13.2 divided by 1.5. 13.2 divided by 1.5. So this is 8.8. Then RC is going to be 3 times. The other one was 3.02. 3 times 3.02, which is 9.06 or 9.1 ohms. A student suggests that RA, RB, and RC should be all equal. State whether your results support this suggestion. Justify your statement with reference to values from your results. So first of all, I will check the percentage difference in the highest values. So percentage difference is going to be, the highest is 9.1, the lowest is 8.6. I divide by the highest, or you can divide by the average. So I will divide by the highest, which is 9.1. Or let me divide by the average. The average is 9.1 plus 8.8 plus 8.6 divided by 3. So the average is approximately 8.8. So I can divide this by 8.8. Then I will multiply this by 100. So I want to see the percentage difference. 9.1 minus 8.6, that is the highest minus the lowest, divide by 8.8, then times 100. So this is approximately 6%. So this is approximately 6%. So it is within the limit of experimental accuracy, which is 10%. So I'll simply say yes. The reason is the largest and the smallest values. The largest, that is 9.1 ohms, and the smallest, that is 8.6 ohms. The largest and the smallest values are within 10% limit of experimental accuracy. So the largest value, which is 9.1, and the smallest value, which is 8.6 ohms, are within the limit of experimental accuracy. Within the 10% limit of experimental accuracy, because the percentage difference between them is 6%, which is less than 10. So they are within the limit of experimental accuracy. So the suggestion could be correct. A student investigates the resistors in circuit A using a variable resistor to change the current in the circuit. In the space below, draw the symbol for a variable resistor. So we need a variable resistor. So that is a variable resistor. Suggest one advantage of using a variable resistor to change the current in the circuit. Of course, a variable resistor has several advantages. For example, it can easily set the current to the exact chosen value. You can easily set current to the exact chosen value or exact chosen values. That is very number one. Or you could say it is easy to obtain a range of values of current. Easy to obtain a range of values. It is easy to obtain a range of values of current. Or you could even say, these are just alternatives I am giving, more straightforward to change. It is a more straightforward method to change the current. More straightforward method to change current. So instead of saying is it obtain a range of values of current, you could also say a continuous set of data can be obtained. Continuous. What is the spelling of continuous? Set of data can easily be obtained. When you use a variable resistor, you can get a continuous set of data easily. So it is easy to obtain a range of values of current. You can easily set a current to an exact chosen value. It is a more straightforward method to change current. Any of those is an advantage, but most of them refer to almost the same thing, so you don't state more than one. Question 3, a student determines the focal length of a converging lens by two methods. We have the diagram here. The student sets up the apparatus as shown in the figure. Suggest one precaution that must be taken when setting up the apparatus to ensure accurate measurement. So first of all, from your classroom, from your classes, your teacher must have mentioned that the lens, the object, the lens, and the lamp are supposed to be at the same height. So number one, you can say the lamp, object, and the lens must be at the same height. The lens, object, and the lamp must be at the same height if you want accurate measurements. Number two, you can now talk about the screen must be perpendicular to the bench, or the screen and the lens must be perpendicular to the table or the bench. So we will say the lens and the screen must be perpendicular or at right angles, perpendicular to the bench. So if the lens is bending towards one end, then the measurements are not going to be accurate. Alternatively, you could fix, because you want to measure the length using a ruler, you could fix the meter ruler to the bench. So fix the meter rule to the bench. Instead of holding it in your hands to cause parallax error, You would fix the meter rule to the bench to avoid parallax error. Okay, the student sets the distance u between the illuminated object and the lens to 20.0 centimeters. He places the screen near the lens and moves the screen until a sharp image of the illuminated object is seen on the screen. Describe a technique for obtaining an image that is as sharp as possible. Of course, if we want an image as sharp as possible on the screen, we have to move the screen forward and backwards until a bright spot is seen on the screen. So the technique is very simple. Move the screen slowly back and forth. Move the screen slowly back and forth to locate the position where the image formed is sharp. So you must move the screen slowly back and forth, and you will notice that there will be a point. There will be a point between the lens and the position of the screen where the image formed on the screen is extremely sharp. So that will be the best position for the image. Then measure V1, the distance from the lens to the screen on the figure 3.1. So because the paper is on a computer which is 14 inches and I've fitted into the page of the computer, so I may not get exactly what is expected, but you just put your ruler there. I'll give an estimated value from my computer. So when I measure the length V1 using a ruler on my computer, it is giving me 8.0 centimeters. So V1 is 8.0. Now, of course, I'm getting 8, but any measurement from the ruler in centimeters should be recorded to one decimal place. So it is 8.0. When you write 8, it doesn't make sense. It should be 8.0. Then the figure 3.1 is drawn to a tenth of a scale. What does that mean? It means the measurement we have got V1, which we have got as 8.0, must be a tenth of its actual distance. So it is 1/10 times its actual distance. The V1 which we got as 8.1 is 1/10 of its actual distance. So the question wants us to find the actual distance. So if 8.0 is 1/10 of the actual distance, then it means the actual distance must therefore be 8.0 times 10, which gives us 80, maybe 80.0 in centimeters. So this is going to be 80.0 or simply 80 centimeters. Okay, the shapes of the illuminated object and the image seen on the screen are shown full size in the figure here. This is full size, that is to scale. Measure H naught. So I'll measure this from my computer. I may not get exactly the same value as yours when you print the question paper. Okay, so from my computer, I'm getting 1.2 centimeters. You may get a slightly different value depending on the printed copy that you have. Measure H1, height H1. So I'm measuring H1 from my computer. Okay, so using my ruler, H1 is 4.8 in centimeters. Oh, the units are already given there. So this is a repetition. Then calculate a value. Calculate a value m for the magnification using the equation m is hi over h naught. So the magnification m is going to be hi, which is 4.8 divide this by 1.2. So 4.8 divided by 1.2, this gives me 4. So magnification is 4.0. So magnification, of course, has no units because this is in centimeters divided by centimeters, which cancels out. Calculate a value f1 for the focal length of the lens. Use your values from B Roman 2 and C Roman 2, and the equation f1 is equal to v1 over m plus 1. So f1 is going to be v1. I think we got v1 as, was it 80? Yes, v1 is 80. Centimeters divided by m, which is 4.0 plus 1. So that is 80 divided by 5. I think this is 16. So that is going to be 16 centimeters. Describe one difficulty that is experienced when using a ruler to measure the height of the image in this experiment. Suggest an improvement to the apparatus to overcome this difficulty. So using a ruler, first of all, you need light to see the image. And now if you place a ruler in between the object and the image, then it means the ruler obstructs, or the ruler and the hand get in the way. So number one, the hand and the ruler gets in the way. Get in the way of light. So it means the image disappears when measuring. So of course this creates a shadow. So I'll say creating a shadow. So the hand and the rule get in the way of light when measuring, creating a shadow. How do we solve this? Of course, I'll use translucent. You can use a translucent. That is, translucent means allow some light. So use a translucent screen. Use a translucent screen and measure from the back. So you would use a translucent screen and measure from the back. Alternatively, you could fix a grid to the screen or fix a grid to the screen. So if you have a grid already fixed to the screen where the image is being formed, then there is no problem with this. Alternatively, you could also mark the top and bottom of the image on a screen. And measure later. So you just put a mark on the top of the object and the bottom of the on the top of the image and the bottom of the image, then you can now measure later on. Alternatively, one other difficulty or another difficulty in getting better results could be difficult to keep the rule still and read the scale at the same time. So instead of saying the hand and the rule get in the way of light when measuring, creating a shadow, you could say difficult difficult to keep the rule still and read the scale. It is hard for you to keep the rule scale and read its scale. So this could also be solved by saying fix. You can fix the rule to the screen. Fix the ruler to the screen, so that you just look at the ruler which is already fixed to the screen. So all these are almost answering the same thing. If it is difficult to keep the rule still because a normal human being, the hand shakes. So fix the rule to the screen, and then you just look at the rule when the image is being formed on the screen. As simple as that. Okay, I think that is all. Then F. The student adjusts the position of the lens so that U is 40.0 centimeters and obtains a new value of V2. For the distance between the lens and the screen, V2 equals to 25.1. Now notice that this time V2 is 25.1 and U is 40.0. These are very big values. Calculate a second value, F2, for the focal length of the lens. So let's say F2 is going to be U, which is 40.0 times V2, which is 25.1, divided by U, which is 40.0 plus 25.1. So 40 times 25.1 divided by 40 plus 25.1. So this is giving me 15.4. So F2 is 15.4 centimeters. Let's check again what was F1, 16 centimeters. Okay. Suggest which value of focal length F1 of F2 might be more accurate. I think F2 is going to be more accurate. So I'll say F2 is more accurate. Reason? Because F1 used values of H which were 1.2, 4.8. These are very small values. Small values or small measurements give a large percentage uncertainty, so it means F1 is not very accurate because it uses small measurements. F1 uses smaller measurements. F1 uses smaller measurements of H naught and H, which gives large percentage uncertainty. You notice that F2 was using large values of U and V2, yet F2 was using large measurements, yet F1 used the smaller measurements of H naught and H, which gives a large percentage uncertainty. Every time you take a very tiny measurement, it means the percentage uncertainty is going to be large. But if you take a large measurement, the percentage uncertainty is smaller. So that means a large measurement gives more accurate values. Okay. And lastly is planning. A student investigates the effect of insulation on the cooling of a liquid. So it is effect of insulation on the cooling. For cooling, we must talk about there must be change in temperature. Plan an experiment which will enable her to investigate how changing thickness of insulation. So this is going to be the independent variable because it's the one which is going to be changed by the student. Changing thickness of insulation surrounding a beaker affects the rate of cooling of hot water in the beaker. So the rate of cooling is going to be the same as the rate of temperature change. Rate of temperature change. The apparatus available includes a glass beaker, hot water supply, a lid to fit the beaker, strips of insulation. So if the strips have equal thickness, then I will say I'll use the first, second, third, fourth, fifth strip. I will just go on adding a strip. until I have 5 sets of results. In your plan, list any additional apparatus needed. So for example, I will need the same volume. To measure the volume, I will need a measuring cylinder. Then to find the cooling rate, I need temperature change in temperature, so I will need a thermometer. Because the rate involves time, I will need a stopwatch. I think those are the apparatus I'm going to use here. Explain briefly how to do the experiment, including the measurements to take so that the rate of cooling can be determined. State the key variables to keep constant. So we shall always ensure that the volume of the hot water used is constant, and we should also ensure that the initial temperature is always the same. Initial temperature is going to always be the same. Draw a table or tables with column headings to show how to display the readings. You are not required to enter any readings in the table. Explain how to use the readings to reach a conclusion. So I may plot a graph to reach a conclusion, or may just compare the values in the table. You may draw a diagram if it helps to explain your plan. So I always encourage my students to draw a diagram. So the diagram I will draw, let me draw a diagram here, which is very quick and easy. Let this be the table or the bench. So I'm going to put here the cylinder, not the cylinder, the beaker. The cylinder has been, the beaker has been covered with a lid. Then I'm going to wrap this with an insulating material. So this is the insulator. This is going to be the lid. This is going to be hot water. Oh, there's one thing which is missing, and that is going to be the thermometer. I think that is a simple diagram. You have an insulating strip, hot water, you have lead, and the thermometer. That is a simple diagram for this experiment for your level. You can draw a better diagram, better than mine. I don't care. What I'm interested in is in the explanation here. So number one, you were able to identify which one is going to be the independent and the dependent variable. So you can tell the examiner that in this experiment, the thickness of insulation is the independent variable. and I will just say the rate of temperature change, and the rate of temperature change or the rate of cooling is the dependent. Remember, an independent variable is the one which you change as the experiment, and when you change it, the dependent automatically changes on its own. So the rate of temperature change or the rate of cooling is the dependent variable. So number one, I'm going to take one strip of insulation and wrap it around the beaker. So take one strip of insulation and wrap it around the beaker, and wrap it around the beaker. Number two, I'll now pour some hot water because I need to know its volume and I keep it constant. I'll first pour it into a measuring cylinder. Pour some hot water into a measuring cylinder and record its volume. Then transfer it into the beaker. Remember, the volume of hot water used must be kept constant throughout the experiment. So I'll write it here. The volume of hot water used must be kept constant throughout the experiment. Okay. Then the next thing we are going to measure and record the initial temperature. I'll call it theta naught of the water using the thermometer. Measure and record the initial temperature, theta naught of the water using a thermometer. Measure and record the initial temperature, theta naught of the water using a thermometer. And also remember, the initial temperature of the water should always be constant or should be kept constant. So the initial temperature of water should also be kept constant throughout. It should also be kept constant throughout the experiment. In other words, cooling should always start from the same temperature even when you change the insulation. So the next thing is going to be to record the final temperature. Record the final temperature of the water. Record the final temperature of the water after a time, after say 5 minutes. After say 5 minutes, after a time of for example 5 minutes, after a time of, for example, 5 minutes measured from the stopwatch. So the next thing is now to determine the rate of temperature change or the rate of cooling. So determine the rate of temperature change from determine the rate of temperature change. Of course, rate of temperature change is equal to temperature change over time taken. Determine the rate of temperature change from rate equals to temperature change over time taken. Temperature change divided by time taken, which I have considered to be about 5 minutes. Then the next thing is, of course, I may need to find the average. So I have to repeat for the same insulation. So I'll say repeat the experiment for the same thickness of insulation and obtain an average value and obtain an average rate of temperature change. So you may need to repeat to obtain an average rate of temperature change. Of course, the remaining thing is just now to repeat the experiment by adding a strip of insulation each time until you have at least 6 sets of results. Now repeat the experiment by adding a strip of insulation each time until you have at least 5 sets of values, until you have at least 5 sets of values. So I can draw the table of results here. I'll just draw it very fast. So here is the table of results. So one column should have thickness of insulation, that is in millimeters. Another column could have maybe final temperature. final temperature, theta, that is in degrees Celsius. Of course, I can't put theta not in the table. Another one can have rate of temperature change. The units are going to be degrees Celsius per minute. Or I can write, let me just write the symbol. I would say the units are degrees Celsius per minute. So I will have 1, 2. By the way, you can draw the table here in the same space as the diagram. 3, want to have 5 rows, 4 and 5. Okay, you don't need to add any more values. Then the last part is how you will reach a conclusion. So I'll set reach a valid conclusion. To reach a valid conclusion, I will plot a graph of, on the vertical, I can put the dependent variable, which was the rate of temperature change. Rate of temperature change on the y-axis against insulation thickness on the x-axis to see the relationship between them. That's number one. Or what other than that, this is another alternative. Or I'll compare readings in the table to see if this if is the most important term in this last part. If you don't add the if, then the conclusion becomes wrong. Compare readings in the table to see if a change in insulation thickness to see if change in insulation thickness produces changes in the rate of temperature change. So that's how you will reach a valid conclusion. Either you compare readings in the table to see if whenever there is a change in insulation thickness, it causes a change in the rate of temperature change, or you plot a graph against of one. Of course, you must mention whichever is on the y-axis and whichever is on the x-axis before you reach a conclusion. So I think that is the end of paper 6. Until next time, bye bye.